Welcome! So today we're going to look at exact equations and solving equations that are almost exact. And then we're going to look at solving fairly elementary second-order linear homogeneous equations. And so those would be questions that we see 6 through 12. But first, let's start with the first-order exact equations and those that are almost exact. All right, so beginning with question 1, we're asked to solve y dash equals 2 plus y e to the xy over 2y minus x e to the xy. So what we want to do is put this in the form. All right, so our first step is put in form p of x and y plus q of x and y times y dash equals 0. Okay, and then test whether this equation is exact by taking partial derivatives of p and q. So let's put it in this form first. Okay, so what we'll do is we'll multiply both sides by that denominator so it appears over there, and then we'll take it over to the other side of the equation. And so then what we get is minus 2 minus y e to the xy plus 2y minus x e to the xy times y dash is 0. Okay, now on the left we have our p. So let's point this out as p is this term and q is this. Okay, and now the test for whether this equation is exact. So I'll write test for exactness is the following. Is p subscript y, where this is the partial derivative of p with respect to y, is that equal to, I'll put equals with a question mark over the top, is it equal to q subscript x? And if it is, then the equation's exact and we can proceed to solve this differential equation for y. Okay, so let's test this now. So p subscript y is the partial derivative of p with respect to y. And so p is minus 2 minus y e to the xy. Okay, now applying this partial differential operator to each of these terms, the partial derivative of minus 2 with respect to y is 0. And then for this one, we have a y there and a y there, so we need to use the product rule of differentiation. So we have 0 minus the partial derivative with respect to y of y e to the xy. All right, so here we have a u, here we have a v. So I'll point that out. And so using the product rule, py is equal to, so we pull one out, so we have minus y times the derivative with respect to y partially of e to the xy, and then we swap those around, but the minus comes along for the ride. Okay, and so now the e to the x should go in front, or e to the xy, partial derivative of y with respect to y. All right, so let's take each of these partial derivatives now. So this one is easy. For this one, we need the chain rule, but we know how that works. When we differentiate x, y with respect to y, we're treating all the other letters other than y as a constant. So we're treating the x as a constant. And so an extra x would come out. And so for this, we get minus y times x, and then times e to the xy. Okay, now for this one, the derivative of y with respect to y is just 1. All right, so this is what we have for p subscript y. Okay, now let's do q subscript x. So differentiating q with respect to x. Okay, this is our q. So we're differentiating 2y minus x e to the xy. And so we get 0 for this one because the y is treated as a constant when we're differentiating partially with respect to x. And so then minus the partial derivative with respect to x of x e to the xy. And again, we need the product rule on this. So we have then, pulling one of these out, so minus x partial derivative with respect to x of e to the xy, and then swap the other way around, but we distribute the minus over this sum. Okay, so we have this, and now we need the chain rule here, but we know how that works. Y is treated as a constant when we differentiate partially with respect to x here. So an extra y comes down. So we have minus x, y, e to the xy, and then this derivative here is 1, so we have minus e to the xy. And let's compare this with this. These are the same thing because we can swap the order of the x and the y. So this is equal to p subscript y, and hence this differential equation is exact. Okay, so we have shown that it's exact. And so now we seek a function lowercase f of x and y. All right, so let's get a new page here. All right, so this is question 1 continued. So we now seek a function f of both x and y such that p is equal to f subscript x and q is equal to f subscript y simultaneously. All right, and so what that is, because p we chose to be minus 2 minus y e to the xy. This is f subscript x, or the partial derivative of f with respect to x. And then we have q equal to 2y minus x e to the xy is f subscript y. Okay, now if that's the case, then, right, so if these two equations hold, then what we have is this. Okay, and so this is associated with the chain rule for partial derivatives when all right, so I'll leave it at that. But okay, so let's go ahead and solve for lowercase f at this point. So let's label the first one equation 1 and the second one equation 2. And so using equation 1, we're integrating. So we'll write integrating, but what we're doing is we're integrating partially. So put that in brackets. Now there's a little subtlety here. When we write this, we have f of x and y equals the integral of p with respect to x partially, but when we write this, we put an ordinary d. But how you know that it's partial is because we have the two variables x and y in it. Okay, so we treat the y as a constant when we integrate here. So let's integrate this now. So the integral of -2 with respect to x is -2x. And the integral of -y e to the xy is minus e to the xy, because if you were to differentiate minus e to the xy with respect to x partially, you're treating y as a constant, and that comes down. Right? So this right here is the partial derivative of this with respect to x. And so going the other way, this is our integral. Okay, and then we have what would ordinarily be plus c, the constant of integration, that in this case, because this is an integral taken partially, the analog or analogy of the plus c is a function. And it's a function, say, g of y. It's a function of y because if we differentiate a function of y partially with respect to x, we get 0, right? Because the y is treated as a constant, and so this would just be treated as a constant, this entire g of y, when we're differentiating partially with respect to x. Okay, so here we have now f of x and y, but we don't know quite all of it because we don't know the g of y. All right, and so now our next step is to differentiate this partially with respect to y because we want to compare this with equation 2. All right, so that will state the motivation here. So we differentiate with respect to WRT y, and I'll say partially, because we aim to compare to equation 2. In other words, this line up here, right? And the reason we want to compare it with that is so that we can get more information on exactly what g of y is. All right, so let's take that derivative of this equation partially with respect to y. Okay, so then differentiating the left-hand side, we get f subscript y. Differentiating the right-hand side, the derivative of -2x partially with respect to y is 0. And the derivative of minus e to the xy with respect to y partially is minus x e to the xy. And then the derivative of g of y with respect to y partially is g dash of y, right? As in the first derivative of that function g of y. Okay, now comparing this to equation 2, because fy is fy, so this has to be equal to this q right here. So by equation 2, minus x e to the xy plus g dash of y is equal to 2y minus x e to the xy. Okay, now what do you notice here? These two items are the same, so we can add that to both sides and it vanishes. Okay, and so then we get g dash of y is equal to 2y. And so integrating this with respect to y, so g of y is y squared plus a constant. Okay, and so now we have all the information we need to construct the function lowercase f. So f of x, y is equal to minus 2x. And then we have, let's write our g next. So plus y squared, we'll leave that c to put on the right hand side, but it'll be a different c. Okay, next let's write this. So minus e to the xy. And then we have a plus c, right? But since our general solution, we can rename this and put this on the other side. And this that I have in this rectangular box is the general solution to the differential equation, or ODE. All right, and so now we've completed that problem. We found the general solution to that ODE in question 1. All right, so let's move on now to question 2. And I'm going to need more paper here. I've got question 3 typed out there, but I don't have the same for question 1. So I'll turn the page over, and we'll now do question 2. Find the general solution. So we've got x plus sine y, and then we have x cos y minus 2y times y dash equals 0. Okay, so this is already in our favorite form. We just have to check that this is exact. So what we'll do is we'll let p be equal to x plus sine of y, and we'll let q be equal to x cos y minus 2y. And we want to differentiate p with respect to y and q with respect to x partially. Check that those are equal. If they are equal, then it's exact, and we can proceed to find our lowercase f. Okay, so differentiating, we have p subscript y equals, now this one differentiates to give 0, so we just have cos of y, and then q subscript x is equal to the partial derivative with respect to x of x cos y minus the partial derivative with respect to x of 2y, but that goes to 0, so I'll just say plus 0 there. All right, now here you do not need the product rule here because the cos y is treated as constant when we're differentiating partially with respect to x, so that can just float through the differential operator. Okay, so we have cos y times the derivative with respect to x partially of x. And this part here is just 1. That derivative is 1. And so we just have cos y. And of course these match, right? This is py, or p subscript y. Okay, so the equation is exact. And we can now proceed to seek lowercase f. Okay, so we seek f of x and y such that f subscript x is p, and so in this case p is equal to x plus sine of y, and f subscript y is q, but in this case q is x cos of y minus 2y. Okay, so let's label this equation 1 and equation 2. All right, so integrating equation 1 with respect to x partially, we have f of x and y is equal to the integral of x plus sine of y partially with respect to x. Okay, now this integral is very easy. We just have a half x squared and then plus x sine of y, because remember we're treating this sine of y as a constant because we're treating y as a constant when we're integrating partially with respect to y. And then we have a function of the other letter, g of y. Okay, and so this is our f. Now we want to differentiate this partially with respect to y. So I'll abbreviate differentiating with di double f. and that's again partially. So we have f subscript y equals the partial derivative of all of that Okay, now let's differentiate this. This goes to 0. So we have 0 plus x times the derivative with respect to y of sine of y, and then plus g dash of y. Okay, now this derivative here is just cos of y, so it's x times cos y. So f subscript y is x cos y plus g dash of y. Okay, and so then we want to compare this with equation 2. So this is equal to x cos y minus 2y by equation 2. Okay, fantastic. So the left-hand side, let's say, is this, and the right-hand side is the one below it. And so you can see that we have an x cos y in both the left and right-hand sides. So subtracting that from both sides makes that vanish. And so we get g dash of y equals minus 2y. So g of y is equal to the integral of this. So minus y squared plus a constant, but we'll leave this off because in the end we just want to write the general solution with a c on the other side. Okay, so now I'm out of paper. Maybe I can grab another one from up here. Okay, so given what we've learned here, we have f of x and y equals c is our general solution. And so what is f? Well, we've got some of it up here, and then we've got the rest of it down here. So f of x and y is equal to a half x squared plus x sine of y, and then our g of y is minus y squared, and this is equal to a constant, and so this is our general solution. All right, let's move on to question 3. Okay, we've got a very simple question here in question 3. So it's solve y minus x y dash equals 0 using methods for exact equations. So let p be equal to y, and let's let q be equal to minus x. Okay, and so differentiating p subscript y is equal to just 1, and q subscript x is equal to minus 1. So these are not equal. So the equation is not exact. However, up here this seems to suggest that we can make it exact, okay, and we can. So what we do is we multiply by an integrating factor that we don't know yet. So we multiply by I of x and y, and we assume that the result is in fact exact. Okay, so let's go ahead and do that. So now if we multiply the equation throughout by I, we have, so that's right, we get y times I minus x I y dash equals 0. And so now we let p, and it's not the same p as this. So now let p be equal to y times I, and let q be equal to minus x times I. Okay, and so now we want to take partial derivatives, but this time we assume that once we do have an exact equation. So we assume that this is exact. So I'll put in brackets, and we assume exact. All right, so p subscript y is equal to, now we have to use the product here because presumably I is a function of both x and y. So we have y, I subscript y, and then plus I times the derivative of y with respect to y, but that's just 1, so we just have I times 1. Okay, and so this is equal to q subscript x, which is the derivative of this with respect to x partially. Again, we need the product rule. So we have minus x times I subscript x, and then plus the other way around, except the minus sign distributes over the sum. So we have minus I times the partial derivative of x with respect to x, but that's just 1. Okay, so we have this equation, right? And so let's rewrite this. So y plus I equals minus x I subscript x minus I. Okay, and so what we want to do now, let's rearrange this, right? And so we could also write this as x I subscript x plus y I subscript y plus 2I is 0. Which is another way to write that. Now, if we guess, let's guess I subscript x is 0, because we can see that this equation will simplify quite a bit. And if it all works out and we get such an I, well, we know that the result gives something exact, and then we can solve the equation using our methods for exact equations. All right, so we guess I subscript x is 0. And so then when we do, what we have is this part goes to 0, and so we get an equation that we can write as, so y I subscript y equals minus 2I. All right, and so then this is separable, right? So let's write it in such a way so that we can see that it's separable. So we've got y, partial derivative of I with respect to y equals minus 2I. Okay, so we could bring the I down here, bring the y's over here. And so we then have the integral of 1 on I with respect to I is equal to the integral of minus 2. Now the dy goes over there, and we divide by our y. So we have this. All right, now integrating both sides, on the left we have the natural log of I. So ln of I, or log to base e of I, or some people just leave off the base e and write log. Okay, equals minus 2 log of y. I'm in the habit of writing that, but I'll try for your sake to write ln. Okay, ln of y. And then I don't need the plus c here because I'm just trying to find such an I. All right, so let's take this up into the exponent here via a log rule. So this is ln y to the minus 2. And so then, since we have the same base, we get I is equal to y to the minus 2. All right, so that's fantastic because that tells us that this equation up here is now exact with this particular I value. So let's write this y times y to the minus 2 minus x y to the minus 2 y dash equals 0 is exact. Okay, and then on the next page we will simplify that. So simplifying that equation, we have y to the minus 1 minus x y to the minus 2 times y dash equals 0 is exact. So we have forced that equation in number 3 to become exact by multiplying by a function that made it exact. All right, so now that we know that this is exact, we seek a function f of x and y such that p is, which is in this case is y to the minus 1, is f subscript x, and q, which is minus x y to the minus 2, is f subscript y. So let's label this equation 1 and equation 2. Okay, so taking equation 1 and integrating both sides with respect to x partially, we get from equation 1 f of x and y is equal to the integral of y to the minus 1 with respect to x partially. And so that is x y to the minus 1 plus some function of the other letter. Okay, now differentiating with respect to y so that we can compare with equation 2, we have then f subscript y. Just looking at this and differentiating this partially with respect to y. Now we treat that x as a constant when we do this, and we're subtracting 1 from the exponent, right? Bringing down the exponent, subtracting 1 from the exponent. So we get minus x y to the minus 2 plus g dash of y when we differentiate this partially with respect to y. Okay, and when we compare this to equation 2, this is supposed to be minus x y to the minus 2. Okay, now conveniently these two match, and so then g dash of y is a constant, and hence we can just take f as x times y to the minus 1 plus a constant. So x over y and then plus c. All right, now remember that the general solution is f equals a constant, and so hence x over y equals a, or actually let's call it b, is the general solution. Okay, gen solution. All right. Now, let's take this over to the other side. So y equals x over b, and then let's call 1 over b equal to a. All right, so we just have a line. Y equals ax is a nice way to write our general solution to that equation 3. All right, now let's just check, because that was quite involved, wasn't it? So differentiating, or to check, y dash is a, and so let's sub this in. sub this into the differential equation, which was y minus x y dash equals 0. But let's check if we get 0 when we do this. So y is equal to ax in our proposition here, and then minus x times y dash. Now y dash is a. Yes, these are giving us 0. Okay, so all good. All right, let's move on to question 4. So question 4 says convert this differential equation y dash equals 2xy minus x into an exact ODE and find the general solution. So this will be a similar routine. All right. So let's take all of this over to the other side of the equation. So we have x minus 2xy plus y dash equals 0. All right, let's put a 1 in front of this y. Put a bracket around this. So here is our p, and q is 1. All right, now we can see that this is not going to be exact, right? Because the derivative of q with respect to x is 0. So we'll just say is not exact. So what we'll do is we'll multiply by an integrating factor. Okay, and so then we have a new p, right, because I want to distinguish it from these two. New p equals x minus 2xy times I, and then the new q is just I times 1, which is I. Okay, and we are insisting that the resulting equation is exact. So this gives an exact equation because we insist. Or we're solving for I such that the result is an exact equation. All right, so differentiating this p partially with respect to y, so p subscript y equals x I subscript y minus 2x. Now we've got to differentiate partially with respect to y, the product of y and I. Okay, and to do that we need the product rule. So I bring one out, differentiate the other one partially with respect to y, and then swap the order of that. But the derivative of y with respect to y is 1. So the second part of this is just I times 1, which is I. Okay, so let's tidy this up. So p subscript y is x minus 2x y I subscript y, and then minus 2x times I. All right, now q subscript x is equal to I subscript x, and we have insisted that these two equations match. So we'll say since the equation is now supposed to be exact, we have then that x minus 2xy all times I subscript y minus 2x times I minus ix, because I'm taking this over to the other side of the equation, equals 0. Okay, so now, because this is a bit Well, it would look a lot nicer if I subscript y were equal to 0, right? And so it would make solving the rest of it very easy. And we only seek one possible I. We don't need to get all of them. We just need to find one I such that the equation is exact. So we guess, or we choose, to put I subscript y equal to 0. And so what we then get is, multiplying throughout by -1, we end up with 2x times I plus ix is 0. Okay? And so taking this over to the other side, we have the partial derivative of I with respect to x is equal to minus 2x times I. And this equation is separable. So we can take the x's and put them with the x's and the i's with the i's. And so we get the integral of 1 on I di equals the integral of minus 2x dx. And this integral is easy. It's minus x squared plus constant, but we don't need the constant here because we just need one I to work to make this equation exact. So we have natural log, so I'll write ln of I is equal to minus x squared. And so then if we solve this equation for I is equal to e to the minus x squared. So this is the I that makes the equation up here at the top exact. All right, so let's put this together now. So now we have P equals x minus 2xy e to the minus x squared is f subscript x, and we have q equals just I, which is equal to e to the minus x squared, which is f subscript y. Okay, and we need to solve this equation for lowercase f because lowercase f gives us the general solution. All right, so moving on. So we have an equation 1, which is this, x minus 2xy all times e to the minus x squared, and then an equation 2, which is f subscript y equals e to the minus x squared. All right, and so now let's integrate equation 1 as we usually do. And again, that's partially with respect to x. We have f is a function of x and y is the integral of x minus 2xy e to the minus x squared dx. Okay, and so now this is partial, remember. We've got an x and a y in there. Okay, so let's break this up as a sum. We'll expand this and break it up as a sum of two integrals. So we have the integral of x e to the minus x squared with respect to x. And then we have minus the integral of 2x e to the minus x squared. And I'll put the y outside because remember we're allowed to treat that as constant. So let's put that outside the front. All right, now if I were to differentiate e to the minus x squared, I would use a chain rule and it would bring out an extra minus 2x out in front. Okay, and so if I say here then, if I compensate for that with a minus 1/2 in the front, then I can insert a minus 2 there so that these multiply together to give me 1. Okay, now I don't really need to do it here. I do want to put the minus inside so it looks like this. So that'll be plus 2x e to the minus x squared. And then we have minus the integral of 2x e to the minus x squared all times e to the minus x squared. And then we have minus the integral of 2x e to the minus x squared all times e to the minus x squared. And then we have minus 2x e to the minus x squared all times e to the minus x squared. Okay, now I don't really need to do it here. I do want to put the minus inside so it looks like this. y times the very same integral. Okay, and so now this integral, which is the same one here and here, this integral is e to the minus x squared. So we have minus a half e to the minus x squared, and then plus y e to the minus x squared, and then there's a plus a constant of integration. But remember, it's not a constant of integration because we've integrated partially with respect to x, so it's actually a function g of y. All right, and so this is our f. But we need a little bit more information about what this g function is. And so now we need to take the partial derivative of this equation with respect to y so that we can compare it with equation 2. So differentiating with respect to y partially, we have f subscript y equals, now this one goes to 0 because we don't have any y's there. And this we can pull out the front and differentiate y with respect to y partially, and we just get 1 for the derivative, and so we get 0 plus e to the minus x squared for this one, and then plus g dash of y for this one. Okay, now let's compare this to equation 2. So this is equal to e to the minus x squared by equation 2. And so we now see that g dash of y is just 0. And then integrating gives g of y is a constant. Okay, fantastic. So then our general solution, remember it's f equals a constant, being a different constant than this, but we can call it c, or a, or b. So we get the general solution, and let's factorize this. So e to the minus x squared outside of y minus a half equals c. That should be our general solution to the differential equation we were given in question 4. All right, so that brings us to question 5. So solve this differential equation using methods for exact equations. Okay, so we want to put this in the correct form. So we'll put a bracket around this and say p equals t squared minus x, and q is equal to minus t. Okay, now remember we used to differentiate with respect to y. We used to differentiate p with respect to y, but the dependent variable is x in this case, and the independent variable is t. So now in this case, we need to calculate p subscript x to test whether this is exact. So p subscript x is equal to minus 1, and q subscript t is equal to minus 1 also. So the equation is exact. And that should make this easy. All right, and so now we seek lowercase f of the t should come first because let's do this in alphabetical order, t and x, such that p is equal to f subscript t and q is equal to f subscript x. Okay, so what is that then? So f subscript t is equal to t squared minus x, and this is our equation 1. Equation 2, f subscript x is minus t Okay, now integrating equation 1 with respect to t partially. So integrating, and let's just say equation 1, we have f of t and x equal to the integral of t squared minus x dt. And so this integral is 1/3 t cubed minus t times x plus some function g of the other letter. And so in this case, the other letter is x. All right, so this is our f of t and x. Now, differentiating with respect to the other letters so that we can compare with equation 2. So we want to differentiate this partially with respect to x. We have f subscript x is equal to 0 for this piece, and then minus t for the derivative of minus tx partially with respect to x. And then we have plus g dash of x. Okay, and this is meant to be minus t. Now we can see that these two vanish in the equation, and so we get g dash of x is 0, which gives us g of x is just a constant. Okay, then now we know that f of t and x is equal to 1/3 t cubed minus t times x, and that's equal to another constant, say a, and this right here is our general solution to the differential equation we're given here. Okay, let's move on to question 6. And now in question 6, what we will begin is we'll begin to solve homogeneous, meaning 0 on the right-hand side, linear differential equations of degree 2, or order 2, I guess we should say, because the order is the greatest number of dashes that you have there. Okay, so let's say this is a linear second order homogeneous differential equation, or ordinary differential equation, ODE for short. And so what we do with these is the first step we take is to view this in the following way. So a y double dash plus b y single dash plus c times y equals 0. And so here a would be 1, the coefficient of y double dash. B would be 0 because there are no single y dashes in there. And c would be minus 1. Okay, so we recognize what we have here. And so now what we need to do is write down the characteristic equation. So we say the characteristic equation is, now what we're doing here is we're replacing all the y double dashes with lambda squared. And we seek to find lambda. So lambda squared, right, because we have 1 times lambda squared there. And then there are no y dashes, so we have 0 single lambdas. And then we have minus 1 is our c. And there are no dashes in this last one, so we just have a single minus 1 there, equals 0. And let's say which is the equation lambda squared minus 1 equals 0. So what we want to do here is solve for lambda. So we get lambda plus 1 times lambda minus 1 equals 0. So having factorized the left-hand side, so that lambda is equal to plus or minus 1. But let's put lambda 1 is minus 1 and lambda 2 is plus 1. Okay, and so because we have two distinct real roots, which we can decide based on the discriminant of our characteristic equation. So let's write down here that delta is b squared minus 4ac. In this case, we have b squared is 0 squared minus 4 times 1 times minus 1 equals 4, which is positive. So we expect two distinct real roots of the characteristic equation. And so also when we have two real roots or a positive discriminant delta, we know what the general solution looks like. Okay, so we have then y as a function of, say, t. We have a constant a times e to the power of lambda 1 t plus b e to the power of lambda 2 times t. Okay, and in our case, we've got lambda 1 is minus 1 and lambda 2 is 1. So y of t in this case is a e to the minus t plus b e to the plus 1t. And this is our general solution to the differential equation. So this is the general solution. Okay, great. Let's move on to question 7. And let's have a look at this. We have a y dash in this case, so we have coefficients 1, 2, and 2. All right, and so the first thing we want to write is the characteristic equation. So it's lambda squared plus 2 lambda plus 2 equals 0. Now let's form the discriminant delta. So delta is b squared minus 4ac. In this case, b is 2, so 2 squared minus 4 times 1 times 2. And so we have 4 minus 8 is minus 4, and that's negative. And since it's negative, we're going to have a solution that looks somewhat different. The roots of the characteristic equation are not going to be real. They're going to be complex roots. Okay, and so let's find this using the quadratic formula. So we've got lambda equals negative 2 plus or minus the square root of delta, which is minus 4, all over 2 times a. Okay, now simplifying this, we've got minus 2 plus or minus root 4 times root minus 1 all over 2, but we call the square root of minus 1 I. Or if you are an engineer, you might call it j. Okay, so simplifying this, the square root of 4 is 2, so both of these numbers being 2 are divisible by 2, so we have minus 1 plus or minus 2 over 2 is 1 times I, where I is the square root of minus 1. Okay, and so now let's name them. Lambda 1 is minus 1 plus I, and lambda 2 is minus 1 minus I. Now, you can set this up in the way that we did before and call it a times e to the lambda 1 times t plus b e to the lambda 2 times t, but what you'll find, oh, I see, that should be I, right? Yeah. What you will find is that you can express this using cos and sine, all right? And so using the fact that e to the theta I is cos theta plus I sine theta, we know that we can write y as a function of t is equal to a e to the alpha t cos beta t plus, oh no, I need the a in here, don't I? Okay. Plus b sine of beta t, where alpha is equal to the real part of lambda 1 or lambda 2. The real part will be the same, and in this case the real part is minus 1. Okay, so we'll put minus 1, and the imaginary part beta im of lambda, and so in this case the imaginary part is 1 here and it's minus 1 here, but we'll take the absolute value of that and just put 1. Okay, and so then our general solution looks like this. Y of t equals e to the minus t outside of a cos of 1 times t, so cos of t plus b sine of t. Okay, so there's our general solution for question 7. All right, now question 8 is an IVP, or an initial value problem. So we're going to solve this in the same way, but this time we have y of 0 is 1 and y dash of 0 is minus 1. So these two initial values give us a way to find the a and b, or the constants of integration. All right, so let's begin with the characteristic equation. So the characteristic equation that looks like a G, I want to make a Q, is lambda squared minus 3 lambda minus 5 equals 0. Okay, now does this factorize nicely? No, it doesn't, because 5 is prime, which is 1 times 5, and the difference is not 3 or minus 3. So let's use the quadratic equation here, but we need to find the discriminant first. So b squared minus 4ac, in this case we have minus 3 squared minus 4 times 1 times minus 5. Okay, so minus 3 squared is 9, minus 4 times minus 5 is 20, so we get 29. And that's positive, so we know that the structure of our solution is a e to the lambda 1t plus b e to the lambda 2t. Okay, so now let's use our quadratic formula to find the two lambda values. So lambda equals negative b, so plus 3 plus or minus the square root of, well, delta, but that will be root 29. And then that's all over 2 times a, or 2 times 1. Okay, and so now let's name these. Lambda 1 is equal to 3 plus root 29 on 2. And let's set lambda 2 equals 3 minus root 29 on 2. All right, and so now we can express our general solution. Y of t is equal to a e to the power of 3 plus root 29 on 2, and then times t, plus b e to the 3 minus root 29 on 2 times t. Okay, and now what do we do with these initial values? Well, the first thing we can do is sub in 0 for t. So y of 0 is equal to a e to the 0. A e to the 0 is 1, so we just have a times 1. Same thing over here, e to the 0 is 1, so we just have a plus b, and that's meant to be by this equal to 1. Okay, and this gives us one equation. Now, for the other one, we need to differentiate this right here. So differentiating, we have y dash of t, because this is given as in terms of y dash of 0. So we need the derivative of this. And so when we differentiate this, we bring down that constant next to the t, and so we have a times 3 plus root 29 all over 2 e to the power of 3 plus root 29 all over 2 times t, and then similarly for this one. So plus b 3 minus root 29 all over 2 e to the 3 minus root 29 over 2, and then times t. Okay, and so now y dash of 0 is equal to, just looking at this, if we put in a 0 for the t, we have e to the 0, which is 1. So we have a 3 plus root 29 over 2, and then same story over here, b 3 minus root 29 all over 2, and this is equal to, by this initial value, this is equal to minus 1, and this is our second equation. So we have two simultaneous linear equations in a and b to solve. Okay, but let's do this via substitution, because this right here, we can express this as b equals 1 minus a. Okay, and so now we can substitute everywhere where we see a b, we can put 1 minus a. So we get a times 3 plus root 29 over 2, and then plus 1 minus a, 3 minus root 29 all over 2, and this is equal to minus 1. Okay, and now we can solve this equation for a. So what we will want to do here is expand this and collect like terms in terms of a. Alright, so if I multiply the 1 times this, I just get this. I will want to take that over to the other side of the equation. And so let's do that. Equals minus 1, and then we're going to get plus minus 3 plus root 29 over 2. Okay, now when I do minus 1 times this, I also get what is here, but I need to add it to this. And so it'll be a all outside of 3 plus root 29 on 2, and then plus minus 3 plus root 29 on 2. Alright, now the 3's in this will vanish, and we'll get 2 of the root 29's, and so this gives us 2 root 29 on 2, which is root 29. So a is equal to 1 on root 29 when I divide that by on both sides. Now let's simplify this, putting this over one fraction bar. So minus 1 is minus 2 over 2, and minus 2 minus 3 is minus 5. So minus 5 plus root 29 over 2. Okay, now we might want to simplify this a little bit, right? So let's multiply top and bottom of this thing by root 29. So then what we'll get is 29 minus 5 root 29 over 2 times 29 is 58. Okay, so there's our a, and then our b is equal to 1 minus this. So then we have 1 is 58 over 58, so we have 58 minus 29 minus minus 5 is plus 5, and that is all over 58. All right, now 58 minus 29 is 29. Okay, so b is the algebraic conjugate of a. So we can describe that a little bit easier as the algebraic conjugate of a. All right, and that gives us our solution to the differential equation. So let's move on now to question 9. Okay, now in question 9, we just have a very simple looking homogeneous equation. This time we've got dependent variable x and independent variable, let's call it t. Now some people like to put double dots over the x's when they're saying that it's differentiated with respect to time t. But I don't like that because I find them hard to see, especially in small type. Okay, so let's rewrite this. X double dash minus 3x dash plus x equals 0. And the characteristic equation that we get is lambda squared minus 3 lambda plus 1 is 0. All right, now we can see probably that we're not going to get a nice factorization of this. So let's take our discriminant, b squared minus 4ac is minus 3 squared minus 4 times 1 times 1. And so we have 9 minus 4, which is 5, right? 9 minus 4 is 5. All right, so we're going to have our solution in terms of root 5. So using quadratic formula, we have lambda equals negative b, so that's 3 plus or minus the square root of delta. So root 5 all over 2 times a, so all over 2. And so lambda 1 is 3 plus root 5 all over 2. And lambda 2 is 3 minus root 5 all over 2. Okay, so given that, we can express our general solution as x as a function of t is equal to a e to the lambda 1t, so 3 plus root 5 all over 2 times t, and then plus b e to the 3 minus root 5 all over 2, and then times t. Okay, and so we're done with that. We have answered the question. So let's move on to the next one, which is question 10. Find the general solution to x double dash plus 25x is 0. So the characteristic equation here is lambda squared plus 25 equals 0. Okay, we can see that our discriminant is negative. So delta is 0 squared minus 4 times 1 times 25. So we have minus 100. Okay, that is negative. So we have complex solutions to the characteristic equation, not real ones. But we can factorize this over complex numbers or Gaussian integers because it'll be an integer times I. So we can write this as lambda plus 5i times lambda minus 5i equals 0. And then so we get lambda equals 0 plus or minus 5i. Okay? So it's not real. All right, now what is the real part of this? The real part of lambda is 0, and this is our alpha. And the imaginary part, beta, we'll just take the absolute value of plus or minus 5, and we get 5. All right, now remember our general solution here. We have x as a function of t is equal to e to the power of alpha times t. So 0 times t. And then a cos of beta t, so a cos of 5t plus b sine of 5t. All right, and so x of t is, because e to the 0 is 1, we just have a cos of 5t plus b sine of 5t. All right, fantastic. Let's move on to question 11. So in question 11, we've got characteristic equation lambda squared plus lambda plus 2 equals 0. Now the discriminant here, delta equals 1 squared minus 4 times 1 times 2, and this is 1 minus 8 is minus 7, and that's negative. So again, complex, non-real solutions to the characteristic equation. So let's use the quadratic formula. So lambda equals minus 1 plus or minus the square root of minus 7 all over 2 times a. And so we have minus 1/2 plus or minus 1/2 of root 7 times I. Okay, so the real part, so alpha plus beta I, looking at it in this way, the real part is minus 1/2. And so we have our general solution x of t equals e to the minus 1/2 t outside of a cos of the square root of 7 times t plus b sine of the square root of 7 times t. And that's our general solution. Okay, question 12. Solve this differential equation. Again, let's write the characteristic equation. So lambda squared minus 36 equals 0. All right, and so we can factorize this. 36 is 6 squared, so lambda plus 6 times lambda minus 6 equals 0. So lambda equals, lambda 1 is minus 6, and lambda 2 is equal to plus 6. And so we get a general solution given by y as a function of t is a e to the minus 6t plus b e to the 6t, and we're done. But I want to add one more. Okay, so let's make up a question 13. Let's solve y double dash plus 2y dash plus y equals 0. Okay, so here our characteristic equation is lambda squared plus 2 lambda plus 1 equals 0. Now this has a repeated root. Our discriminant here is delta equals 2 squared minus 4 times 1 times 1, and that is 4 minus 4 is 0. So this case is different. So we get a repeated root. And so here our general solution looks like, if I remember right, y of t equals at plus b times e to the power of that lambda we have, which is repeated. Okay, and so we need to solve this. It's a perfect square. We have lambda plus 1 all squared equals 0, so lambda is minus 1 repeated. Okay, so here then we have y of t is a t plus b times e to the minus t. Okay, that's all for now. Thanks.